So as mentioned, I work for Microsoft Research, which is a part of Microsoft. Let's see, this guy. Maybe. No, let's go here. And one of the things, a lot of the times folks, especially outside the computer science area, aren't familiar with Microsoft Research as much. We have about 1,000 researchers worldwide. You can kind of see in the bottom right-hand corner, kind of, all where the different labs are throughout the world. We have the closest one here is actually in Cambridge in the UK, and we have a couple hundred people there as well. So we do research across the board on many different activities, everything from typical computer science type work, hardware, theory, HCI, everything else in that space. But we cover a lot of these areas. But we also have a group that my team focus on where we look at Earth energy and the environment specifically. Where we, and the three kind of areas that we look at are listed there below about what we call visualizing and experience the data and the information. So beyond just visualization, but actually can you gain something from it? Some interesting things around how do you make the data available, so this is what we're talking about here, and also consuming it. And then obviously collaboration across many organizations. So we really look at, are there new ways to help not only analyze the data, using new technologies, new algorithms, things that we might be developing for the science, for the business side, and be able to use them in the science side. So with all the research that we have going on, there's a lot of technology that will probably never go into products. And so we look to see, are there areas that we can help make a quantum change in that science or in those disciplines more than just kind of incremental type work. I also have a kind of a sister organization in our Cambridge lab that focuses on computational ecology and just environmental science in general. And so they do a lot around predictive models. And so we look at how we apply those to some of these science challenges. And they do a ton of work in this space as well, and have their papers in in Nature and some of the other science journals. But one of the things we're looking with them is how do we take some of these and actually apply them to large data sets. So I want to actually talk about a couple other things as well. One of them is we're currently in this era of what we call the data-intensive science. And it's after we've done the computational part for the last number of years. A lot of that was coming out of the bioinformatics type space and the Beowulf clusters and some of those, a lot of HPC type activity. But now with the emergence of, let's say, cheaper storage, faster networking, and cheaper devices, we're able to start collecting and storing a lot more of this data. And so what can you start doing with it? And so this whole idea of the fourth paradigm was something Jim Gray, one of our researchers, had coined back in 2007. And really it was like, how do you actually start analyzing this information, data mining on it, and actually doing exploration just purely on the data. So Jim actually had a couple, let's say, rules that he kind of lived by. And the scientific computing is really revolving around the data now is a key one. So he was working with many different scientists to see how the technology could be helped in that space, how it could help the science. The other thing was as he looked out further, even in the early 2000s, there's a need to take the analysis to the data itself and not the data to the actual computation. And so this kind of has been a change over the last number of years of how you actually can do the work. So HPC type clusters are great, but most part you actually had to send the data there. And the two other key ones that we actually still live by a lot is this idea of you start with 20 questions. What do you want to know out of your data? And actually come up with 20 questions to actually what you might want to ask of it. And if you do that, it actually helps simplify the actual data structures and how you're going to position the data and make it available to others. Because a lot of times the basic, some of the questions you want are built off of other questions. And it also helps focus not only the scientists but also the developers and engineers on actually delivering the tangible result. And so not try to solve everything, but actually solving something initially. And then another key one, which was kind of iterated this morning as well, which is you go from working to working. Try not to actually create the huge kind of systems and then roll them out. We're now in an era where this needs to go more in a quick prototype and keep evolving it along. It's not going to be perfect, and you know it's not initially, but you need to get going and get the science out. And there's a number of reasons, and I go into that as well. So this also led to a book that we actually helped publish and create called The Fourth Paradigm. It's available actually for free. We worked with not only our researchers but also scientists around the world to actually put in a bunch of articles. And so a lot of this thinking is encapsulated in this book. One of our colleagues, Jeff Dozier, who's at University of Santa Barbara, has done a bunch of work kind of looking at both of these spaces as well, and ended up publishing this article in EOS, combining not only the remote sensing data but local data, and how does all that come together, because you're dealing with data at different scales, different time periods, and how do you make sense of that, and how do you make that available to others. So you know, we keep seeing where this is going to work as we go farther forward. One of the other key things that we've noticed in this time, working with a lot of the different science groups, is that the value of the information increases as it becomes processed or becomes actually, algorithms run along it, cleaned up, done some work on it. And so how can you make that available to others and not have people redo the same types of processing over and over again? And that's a really key thing that we look at, because especially when we deal with folks in academia, sometimes grad students seem like, very cheap and they can just keep working on these types of problems. But how do we move the work farther forward to actually have the science being done and not actually just computing on the data that's there? So making those data sets more readily available. This is something we look at a lot. So the coloring's a little off on there. It's actually supposed to be green instead of yellow. But one of the things we also were doing as we were working through some of these projects, we really started understanding some of these challenges, both on how to get the information from the data itself for Earth and how do you actually have that inform or change people's minds, both on the policy side or on the general public or even other scientists. And vice versa. If you make a change in a policy, how does that affect it and how do you actually track that? So if you look at this kind of diagram on the left-hand side, it's really the more typical academic side. You're getting some sort of data sets, you're doing some analysis, and then you do this part that's truly human, which is you gain an insight from that data and you write it up and you publish it. And that insight is the piece that you actually want to communicate to others. And so one of the things that you have to kind of always go through and think about is how does that get communicated, who am I communicating it to, and in what form should it be communicated? So while papers are great for the scientific research output, having the data made available as well as possibly the software to make it reproducible, but also how do you communicate that to policymakers so that they can actually take some action and actually get that implemented on their side, or even the general public. It can't be in the same form, and so finding ways to do that is kind of key. And we look at that from bringing in multimedia, audio, other types of pieces to actually communicate that scientific insight. The other thing that we learned in doing this was the credibility of the information that you're actually communicating goes up if the data is accessible. So not that they actually have to even know anything about the data, but the fact that it's actually accessible increases the value of the information you're trying to communicate to them. And so, this goes into that part of how do you make that data open or available to others to utilize. And then technology kind of underlines it. So one of the ways also that's kind of just for fun, our Skype, which is now one of our subsidiaries, does a lot now with classrooms and getting information across to not only school children but others. And they have actually a focus on the oceans now. They've been working on that. And since we're in around the Titanic, there's actually a talk by Dave Gallo around the, using the UAVs for interacting with Titanic. So these are the ways also, different ways of getting that material out, getting people to understand about it, and it can be at different levels of, or years of their knowledge. So as we go, as I mentioned earlier about the data and the information that you want to get to, there's three pieces that we really think about a lot that are key. One is the overall discoverability of the information, the accessibility of it, can I actually get to it, can I do something with it, and then the third, which is a key one, which is the consumability of it. Okay, I have access to it now, what can I do with it? And if all three of these aren't actually there, the data is no better than being in a file cabinet and being locked away. And so thinking through how the people are going to consume the information, the data is really key. What applications that they normally use can they pull it into? Is it in a form that makes a lot of sense for them to actually use right away? Is it scientifically valid right away as well? So a number of these kind of come together, and how do you actually serve up your data to do this? So I want to give you a quick story about another group that we'd worked with for a number of years, which a little bit farther ahead than most of the sciences. And I think there's an analogy here for not only the oceans, but also other science domains. So the Sloan Digital Sky Survey was the one to actually pull a lot of different data together from these, from the telescope that they had. They started in '92. They were looking for a solution to make that available. And not only was they wanting to make that data available for science, but they also wanted to actually have it available for the general public. Large data set, if you want to talk about big data, really big data. But what was interesting is the way they produced it and serving it up through a database allowed actually not only the data to be published out and people to query against it, but what it also did is allow them to track actually the usability and how that data was used over the years. So not only the citations of it, but hey, I could get real stats on actually people querying against that, or I could see the web hits from it, so you could actually see how people were using those data sets. And it really kind of went to this thing that we call now the kind of the internet scientists, the scientists that could sit at home and actually do data analysis without ever having to go out in the field or actually go to a telescope, but have access to the data. In the case of Sky Survey, well, the cool part was it's a telescope on 24 hours a day, 365 days a year, and no clouds. And so it changed actually how that science was being done. And while there's a little bit difference in it, because for the most part astronomy data no one really cares about, there's no way to really make money on it, whereas other ones on the terrestrial side is a little bit more challenging. But one of the things that they did within there as they were building a lot of this, and we were working with them on the database side, was how they could target their audiences, but also allow the users to actually have a subset of the data in their own little database, execute on it, run the queries against it there, and then get the results set back. And so we kind of joke partially that it's really one of the first examples of cloud computing. We also did a bunch of work looking at how you visualize that information. So we did this work with Worldwide Telescope. It's a 4D environment to actually allow us to view data sets. And we actually created a way to actually create tours through the data that allowed you to script through it, but also do voiceovers and pictures to actually communicate your science as well. And what was interesting is Alyssa Goodman from Harvard, one of the astronomers there, said she's actually had more people watch the tours that she's created than have read her papers, all of her papers. And so we've been doing also a bunch of things looking at Earth-based data sets. And latest, continue looking at new technologies. These are these Oculus Rift glasses, which allow you to do a 3D environment and moving your head around to actually be able to see where you are within that space. We do a bunch of work also looking at this data in this visualization environment. And so this is just some ocean data that we've been working with both Mbari and folks at University of Washington on. How can the data be visualized and also be made pretty beautiful for others to actually look at the information? So again, not only communicate it, but can use the same tool for analysis as well as communication. So I'll skip over most of that. We've been doing a bunch of work for the last number of years looking at where clouds have come, even at the early point of it. And so we really think that the cloud computing portion is a key piece, and sciences should really be looking forward to that. I'll skip over that one. But it's really easy kind of to create some of these different, get on board and create sites very easily. But the key piece I want to kind of show as well, we've been doing work on this with our scientists internally, and in fact doing some of the work around analyzing data from genetics and in conjunction with the Wellcome Trust to actually look for markers as well. So we have folks that do machine learning, and they've been running against these types of large systems in the cloud to actually do this. Hey. As well as doing weather models. We've started doing, we've had this up for 3 years now, and we don't actually maintain it. We just let it run, pulls the data down from NOAA directly, executes against it. You can actually go out and actually create your own. It'll do a forecast, predictive model. What it gets to as well is we know exactly how much it costs to run that each time. And so essentially you can think of it as knowing the cost of your, what you want to run against and what it'll cost every single time for you to do your science. The other key one that we've been doing is actually how do you get to data and pulling it out. And so in this case, we've been doing some of the work, our folks in Cambridge, through Fetch Climate, had pulled in some of the wave energy data. We have a different interface to actually allow you to pull it in. Choose the time set that you're looking at, where you want to do it on the boundary area, and then in this case, you can look at the different data sets very quickly. So the average wave height, this is the period, the energy. But what's key about this is that not only can you download it very easily from essentially almost a notepad, but we have APIs against it as well to make it much easier to get to. On the cloud side, we actually think that this is a huge opportunity for running these types of systems. You get a higher bandwidth on the back end, and so we've been doing it within our researcher efforts, but also we're working with external scientists and researchers as well. And one of the things we started up was a program for researchers to actually utilize these cloud services. And so we do a year of work, free access to Azure to actually run these services. And if you're interested at all, let me know. It's the type of thing where we actually then bring in other technology as well and see how we can actually move these sciences forward as much as possible. So I think I'm done and on time.
Excellent.
Good. Thanks.